So I want to do an example now that incorporates both the idea of the PV diagram and the first law of thermodynamics. So we have here a PV diagram for an ideal gas. They give us the number of molecules. They tell us it's in a sealed container, and it undergoes this process from initial to final here. The question is, how much heat is transferred to or from the gas in this process? Okay, so how much heat is transferred? So we're looking for Q. So Q equals. And what do I know? Well, I know whatever I can figure out from this PV diagram. Right? Well, I also know the first law of thermodynamics, which is that the change in internal or thermal energy of the system is equal to the heat added to the system minus the work done by the system. Okay. So if I could figure out the thermal energy change and the work done on the system or by the system, I could use both of those to find the heat added. Right? Well, okay. So I know a way to get delta E thermal. We've done this in the past. It's 3/2 NK delta T. It would be tempting to say, because in the past we've related this directly to heat added to the system. But again, I can see from the PV diagram that there's also work done by the gas, because that's the area of this PV curve. And there's definitely area here, right? You can see there's some area under there. So I need both of these. So I'm going to find both of these and then plug it into the first law to find Q. Okay. So delta E thermal equals 3/2 NK delta T. Well, I need temperatures first. So for part one here, again, we'll just label it find delta E thermal or delta E internal. So I need the temperature, initial and final, to find a delta T. So I'm going to use the ideal gas law twice. So P initial, V initial equals N KB T initial. Okay, so I can plug into that. Oh, but look, the units on my axes are wrong, right? Or they're not SI. So how do I convert? Well, the kilo, let's use a different color. The kilo is just a 10 to the 3, so there's 10 to the 3 to make it pascals, which is the SI unit. And the volume is multiplied by 10 to the minus 6 to get it in cubic meters. So we'll put those Pascal in cubic meters. Okay. That's pretty straightforward. And then I'm just going to plug in. So the initial pressure looks like 200 times 10 to the 3 pascals times the initial volume is 300 times 10 to the minus 6 cubic meters equals in. They gave me in directly 5 times 10 to the 22 times the Boltzmann constant, which is 1.38 times 10 to the minus 23 joules per Kelvin times T initial. Whew, okay, that's great. So T initial turns out to be 86.96 Kelvin, which is pretty cold. So this is an interesting system. You can do exactly the same thing for final. P final, V final equals NK T final. And again, you can read those pressures off. The pressure is higher and the volume is smaller. So that's useful. Again, 400 kilopascals and 100 cubic centimeters. So instead of writing out that line, I will just tell you the final temperature is 57.97 Kelvin. Okay, so we've got T initial and T final. So now I can plug in to find delta E thermal. Delta E thermal is 3/2 in kb delta T. So that's 3/2 times 5 times 10 to the 22 times 1.38 times 10 to the minus 23 times T final is 57.97 minus T initial is 86.96. And what I get for that is negative 30. So pretty clearly, this problem was built around that 30 and not around the temperatures. Okay, so we're about a third of the way there. So what else do we need? I'm going to erase a little bit of this just to give us some space, since we've already done the work. So part 2 here is the work done by, and remember, work done by is an area. It's the area under this curve. So that's this and this. So I need the area of that. What is that? A trapezoid. How do you find the area of a trapezoid? Well, turns out to be the height times the average of the bases, but this trapezoid is sitting on its side. But you know what? It's easy enough to remember how to find the area of a triangle and a rectangle, right? So there's my rectangle, and there's the triangle. Those I can remember off the top of my head as well, fairly readily. So we'll just say equals area. So what is the area? Well, it's the area of the triangle plus the area of the rectangle. So the area of the triangle is half base. The base is delta V times height, which is kind of a delta P, right? Let's just do this. Let's just do that in one step. So it's half the base. The base is 300 minus 100. That's times 10 to the minus 6 cubic meters, times the height, which is 400 minus 200 times 10 to the 3. All right, plus the rectangle, which is just 300 minus 100 times 10 to the minus 6. Times 10 to the minus 6 times 200 minus 0 times 10 to the 3. Okay, so what this turns out to be is 60. But we're going backwards. Delta V is actually negative, so I should have been careful. Maybe I could have said 100 minus 300 for the volume change. But either way, if I just find the area, and remember when I'm going backwards, that area is negative. So let's underline that. Again, the way to conceptualize this is to say, if the gas is contracting, if delta V is negative, something is doing work on the gas. So the gas is doing negative work. Okay, so then part 3 here is that the change in internal energy is Q minus work done by the gas. So that's 30 joules equals minus 60 joules minus the work done. Oops, backwards. Q minus 60. So what do I get here? Oops. Delta E thermal is negative 30, right? So let's go negative 30 joules, negative 60 joules. Okay, so if we do this math, then Q equals negative 30 then minus minus 60 is actually positive. So then I add or subtract that 60 to the other side, minus 60 joules. The total heat dumped by the system is 90 joules. So 90 joules of heat was exhausted from the system to make this happen. So that's a good example of how a PV diagram can be used to solve heat added to a system, even though heat doesn't show up directly in the ideal gas law or in a PV diagram. Let's look quickly at one other problem, maybe just conceptually. Example 6 here says an ideal gas expands quasi-statically to 3 times its original volume. Let's say it happens one of 2 ways. It can either happen isothermically or isobarically. Which one requires more work from the gas? Okay, so let's draw that on a PV diagram quickly. So here's pressure and here's volume, and we're starting at state 1, right? So P1, V1 at some T1. And then we're going to either do this isothermally or isobarically. So isobarically has us go this way, right? And we're going to 3 times the volume. That looks like roughly 3 times. So this would be state 2. And it could also happen isothermally. So we're going to the same volume. But remember, an isotherm is a curve. It's a 1 over V. So it might look more like this. That's a little ugly. It look more like this. Nope. Can't get my wrist to curve the right way. Go just a little slower. I like the beginning. Sure, that would be good enough. So we could ask which one of these, so this is going from state 1 to state 2, which one of these requires more work from the gas? Well, again, work done by is an area. So pretty clearly, it took more work from the isobar than the isotherm, right? Because the area is bigger for the one that goes straight over than the one that curves down. So the difference here would be in the, let's do this. So P2 V2 equals in our T2, right? The volume change is the same. The volume increases to 3 times what it was. When the if the pressure stays, so let's say volume goes to 3 times volume. If the pressure stays the same, I'm at a higher temperature than in the isotherm. In the isotherm, the temperature stayed the same and the pressure had to get smaller. So the difference here would be you would have to add some extra heat to make this happen isobarically. Okay, so that's interesting. There's some interesting stuff you can do here. You can do some algebra with this. We could actually figure out exactly what that ratio is. But I'll leave that as an exercise for the observer.